we are going to discuss about the first topic in the module 3, that is LTI system properties in terms of its impulse responses. Okay, so in the module 3 we have like two portions. One is the LTI system properties in terms of impulse response, and the second half is Fourier representations of periodic signals. Okay, so we are going to deal with the first half. In the first half, we have three portions to study. One is interconnections of LTI system. The next one is properties of LTI system. Then the step response. Okay, so we are starting with the first topic, that is interconnections of LTI system. Okay, so we know about what is meant by LTI system. That is the systems which satisfies the linearity property and the time invariance property are known as LTI systems. So how can, like, if we are connecting two LTI systems together, how can we find out the overall impulse response? That's what we are going to discuss. So as we know, like any LTI system, we can connect in two ways. One is a series connection and another one is a parallel connection. So we are going to discuss first the parallel connection of LTI system. So consider this diagram. So in this diagram itself, you can see that we have two LTI systems. First LTI system's impulse response is H1 of t. Second system's response is H2 of t. So both these systems are connected parallelly. So how can I write the output equation? I can write the output y of t as output of the first system plus output of the second system. That is y1 of t plus y2 of t. That's what I wrote here. Okay, now we will see how to write y1 of t equation. y1 of t, I can write it, this is an LTI system. So obviously output of the system is h of t input, convolution, impulse response, isn't it? So I can write y1 of t as x of t convolution h1 of t. That's what I wrote here. Plus second output, that is y2 of t, I can write it as x of t convolution h2 of t. Okay, so like this, I wrote the equations for both y1 and y2. Now, what is x of t convolution h1 of t? We know this equation. This is our convolution integral equation. That is integration from minus infinity to plus infinity x of tau h1 of t minus tau d tau. Similarly, I can expand this y2 also. Okay, so that's what I'm going to show next. That's what I expanded both the equations. I substituted the convolution integral and expanded, so this equations become like this. Okay, now you just see x of tau is common in both these equations. I can take this thing outside, and similarly you can see one more thing. Both the integrals are with respect to tau. So I don't want to represent two integrals. So I'm writing it as one integral minus infinity plus infinity x of tau. I took it outside. Then h1 of t minus tau plus h2 of t minus tau d tau. Okay, so this thing h1 plus h2 term, I'm going to assume it as it is h. Okay, that is h of t minus tau. How I'm writing the t minus tau is because here you can see that it is h1 of t minus tau. Here it is h2 of t minus tau. That is, it's a time shifted version. So even though if I am adding both these signals, I will get a time shifted version of signal only. So I am writing it as h of t minus tau. What is this equation? This is our usual convolution integral equation. So once again, I can write it as y of t is equal to x of t convolution h of t. What this h of t is, it is the sum of h1, that is impulse response of the first system plus impulse response of the second system h2. That's what we learned, that if you are connecting two LTI systems in parallel, the overall response will be the sum of the individual responses. That is, I can represent what is this diagram we assumed here. this diagram we can represent like this, that is the equivalent of the first diagram. This is what if you are connecting in parallel. Now we are going to see if you are connecting two LTI systems in series, how can we write? Okay, so yeah, just see, it is cascade connection of LTI systems. So just consider this diagram. I connected two LTI systems in series. H1 and H2 are in series. So this in between output, I'm going to represent it as Z of t, and the final output, I'm going to represent it as Y of t. Now, how can we write Y of t equation? I can write Y of t as Z of t convolution H2 of t. That's what I wrote. Y of t is equal to Z of t convolution H2 of t. Now, by substituting the convolution integral equation, I can write y of t as integral minus infinity to plus infinity z of tau h2 of t minus tau. That is like normal convolution integral equation I substituted. Now you can see here that you have a term z of tau. What is z of tau? Just see the previous diagram. Z of tau is, or z of t is the output of the first system. So what is z of t? It is x of t convolution h1 of t. Okay, so now I'm going to substitute that also in our equation. So like you know that you don't want to confuse about that z and t, like it is z of t only, but the time axis I'm going to replace it as tau. That is the horizontal axis, x axis is tau now, that's it. Okay, so I'm going to write z of tau is equal to x of tau convolution h1 of tau. That is, again, this I can represent like in this form. Actually, this is in terms of tau. Previously, all equations we wrote in terms of t. So here we need one more extra variable. For that, I'm taking a variable v. Okay, so now you see z of tau, I'm going to write it as integral. This is v. V changes from minus infinity to plus infinity, x of v, h1 of tau minus v dv. Okay, where v is this just variable of integration. This is an extra variable I added. Now this equation number 2, equation number 2 means z of tau equation. This equation I'm going to substitute in the first equation. So are you getting two integrals? One integral will be with respect to tau, another integral will be with respect to v. Okay, x of v, this one, x of v, h1 of tau minus v, then this portion, h2 of t minus tau dv d tau. Now, in this, I'm going to substitute tau minus v. Actually, both these things are extra variables. Okay, so this tau minus v, I'm going to assume it as a new variable eta. Okay, so like what will happen here is like this thing x of v, I'm not going to change anything. This thing will become h1 of eta here. This portion will become h1 of eta, and this portion will become, this is h2 of t minus, here from this equation I can write tau is equal to eta plus v, that is this minus is outside, so minus v minus eta d eta dv. Okay, now just see, only consider this inner integral alone. Okay, actually this inner integral varies with respect to eta now. So now just assume this integral alone. It is h1 of eta, h2 of t minus v minus eta. So can we write this equation as like in this form? Like see, h1 of eta, h2 of t minus v eta d eta. I'm going to assume this thing as h of t minus v. Why I wrote this thing is, just go back and see your convolution integral equation. It is y of t, how I wrote it is z of tau h2 of t minus tau. h2 of t minus tau, this equation I wrote it as this is y of t. So obviously here you see H2 of T minus V minus eta d eta I can write it as in terms of T minus V, isn't it? So instead of this thing, I wrote it as Y, but here I'm going to assume this thing as H. So simply I'm writing like H of T minus V. Now this equation, that is like instead of H1 of eta, H2 of T minus V eta d eta, I'm going to substitute this thing as H of T minus V in the previous equation. So this equation will become, this integral is there obviously, minus infinity plus infinity, X of V, this entire thing, I can write it as H of T minus V dV. Now you can see that this equation is also in the form of convolution integral. Actually, for convolution integral, we wrote in terms of or with respect to tau. Here we are going to write the equation with respect to V. That's it. No other changes. So this, you can see here that if you are connecting two systems in series, just like this, if you are connecting two systems in series, the overall response is in the form of convolution. Previously, if we wrote it in terms of parallel or parallel connection, we got that the overall response is the sum of the individual responses. But from here, we saw that, see, this equation is in the form of convolution integral. That is, if you are connecting two systems in cascade, the overall response will be convolution of their individual responses. Okay, so we discussed about both the interconnections, that is cascade connection and parallel connection of LTI systems. We will see some problems from this part. Just see what like the question says is, like they are going to give the individual impulse responses H1, H2, H3, H4. They are telling us to find out the overall impulse response H of n, that is this entire thing. Okay, so this thing we have to find, this entire systems of response we have to find, that is input is X of n and output is Y of n. This thing we have to find out. So from this diagram itself, we will write the equation first. You just see H1 and H2 are in parallel. That is, I can write this overall response equation as H1 plus H2. Then this H1 plus H2 I connected in cascade. That is H1 plus H2 convolution H3. Now this thing I am connecting in parallel with H4 means my final equation will become, see, Y of n is equal to, sorry, this is not Y of n, this is H of n. H of n is equal to, see, H1 of n plus H2 of n, because they both were in parallel. Convolution H3 of n, that is they were in series. Then here, come back to the previous one. See, this H4 is here, it is minus symbol. So obviously in the equation also I have to write it as minus. So that's why this minus came, minus H4 of n. Now, already in the question itself, they provided the values of H1, H2, H3 and H4. I'm substituting that. Okay, H1 was Y of n, H2 was U of n plus 2 minus U of n, H3 was del of n minus 2, H4 was alpha power n U of n. I substituted all these things. Now you can see that U of n and this U of n will get cancelled. So I'm getting U of n plus 2 convolution del of n minus 2 minus alpha power n U of n. Now you see this, actually we can apply one property of the convolution sum, that is U of n plus 2 convolution del of n minus 2 will be U of n plus 2 minus 2, that is U of n itself. So this entire thing I can write it as U of n minus alpha power n U of n. If you want, you take that U of n outside and write the final answer. Okay, so this is about the first problem. We'll see the second problem. Here also they gave a little bit bigger circuit diagram and they are telling us to find out the overall response. Okay, so Now you just see these two are H3, H2 and H3 are in parallel. H1 and H4 are in series. So here it will be H1 convolution H4. That's what I wrote. H1 of T convolution H4 of T. Then this is minus. So minus of H2 plus H3 will come because they are in parallel. So I took that minus inside. So it is coming as minus H2 of T minus H3 of T. Then this entire thing is in series with H5. Then this convolution H5 of T. This is how we are getting the overall response of this question. Now we'll go to the third problem. Just see, they are giving the values of H1, H2 and H3. They are telling us to find out the overall impulse response of this circuit diagram. Okay, so now you see H2 and H3 are in parallel. That is, I have to write it as H2 of N plus H3 of N, and this entire thing is in series with H1. So convolution H1 of N. So I got the overall response equation. Now substitute the values of H1, H2, H3. I substituted all those things. So you are getting like 1 by 2 all power n u of n plus 2 convolution H2 was del of n, H3 was u of n minus 1. Now I am applying the distributive property. So expanding these terms. So I am getting like this 1 by 2 power n u of n plus 2 convolution del of n plus this. So here it is step function convolution with del impulse function. So obviously I can write the answer within one step. So this answer I will get it as 1 by 2 power n u of n plus 2. But come to this side. It is step function. This is u of n plus 2 is a step function. U of n minus 1 is also a step function. I cannot get an answer within a single step. We need to solve this term by using convolution sum. So first represent both the waveforms. This is 1 by 2 power n u of n plus 2. It is u of n plus 2. That's why it is starting at minus 2. And this is u of n minus 1. It is n minus 1 delayed version. That's why it is starting at 0. It's starting at 1 instead of 0. Now do the convolution. That's what, like I can write this thing 1 by 2 power n u of n plus 2 I'm keeping as a constant sequence x of k, and this I'm going to keep it as h of n minus k, that is time shifted cases. Okay, so you know that this point obviously we used to mark it as k is equal to n minus 1. So this point, first I'm going to move in this side, that is negative side. That is, I'm going to think that this n minus 2 is less than minus 2. If n minus 1 is less than minus 2, I will not get any overlap at all. Then my answer will be 0. I'll get an overlap when this n minus 1 is greater than or equal to minus 2, because my first signal starts at minus 2. That's why. So this I can rearrange and write it as this minus 1 will come this side. That is n greater than or equal to minus 1. So I can write my convolution equation as y of n is equal to k varies from minus 2 to n minus 1. That is, like I'll get an overlap up to where this n minus 1 value is there. N minus 1, x of k, h of n minus k. What is x of k amplitude? X of k amplitude is 1 by 2 power k. Substitute that. H of n minus k amplitude is always constant. It is 1. So I substituted both the things. Now, like we have to make this lower limit as 0. So I'm doing the computation in that way. That is, I'm going to substitute m is equal to k plus 2. So the lower limit will become 0 and the upper limit will become n plus 1. Now this is in the form of summation n varies from 0 to n alpha power n. It is 1 minus alpha power n plus 1 divided by 1 minus alpha. Substituted that, I'm getting this equation. I just simplified. I'm getting this equation. And now you come to the case. Here we assume that the n minus 1 is greater than or equal to minus 2. That is, n is greater than or equal to minus 1. So that is like I'm assuming that n is greater than minus 1. So your signal I can write like this. It is u of n plus 1 because you said that your n value is minus 1. It starts at minus 1. So obviously it is a delayed version. It's actually it is not delayed. It is a time advancement because it is starting at minus 1 means I should write it as n plus 1. Then only my signal will start at minus 1, isn't it? So that's why I am writing this entire thing as this 1 by 2 power minus 3 is 8. 8 minus 1 by 2 power, this thing will become n minus 1. This as u of n plus 1. Now substitute this thing in your overall impulse response equation. This is what your answer is. Okay, so this is all about the interconnections of interconnections of systems and interconnections on systems and problems related to interconnections of LTI systems.